Okay, so stoichiometry and precipitation reactions. So all we're doing is we are going to stoich this out and figure out how much can be made, how much of our solid can be made. So first of all, the question says, calculate the mass of silver sulfide produced when 18 grams of silver nitrate is added to excess sodium sulfide. So a lot of stuff going on here. So first thing we have to do is we have to write the equation. So we know mass of silver sulfide produced. So that is going to be on the other side of my arrow. Ag2S. And we want to know how much of that is produced. When silver nitrate, so AgNO3, is added to excess sodium sulfide, Na2S. And we know we have 18 grams of silver nitrate. But we're not done because we have a double replacement going on here. So our other product is going to be sodium nitrate. And then you're going to have to balance it. So we need a 2 here and a 2 here. And we're going to stoich from 18 grams to however many of silver sulfide. So start with what we know. We know that we have 18 grams. So you need your calculators out. 18 grams of silver nitrate. It wants to know, so we need to change that to moles. So we need moles, grams of silver nitrate. I already have that down for you guys. So it's 169.88 grams of AgNO3.
When we're writing these on like the test, do you want us to write AgNO3 on like everything we get silver nitrate? Do you just write grams and moles?
I would say get used to writing it just because I don't know how they grade the AP exam. They'll probably just look at your work and see if you knew what you were doing. But it could be, do you get a point or not if it's there or not. So I would just get used to writing it. Now we're in moles of silver nitrate, and we need to get to moles of silver sulfide. So we need the mole ratio. And for every 1 mole of Ag2S, we have 2 moles of AgNO3. Yes?
I thought that the top was supposed to cancel out with the bottom. So is that different when you do the ratio?
My top over here is canceling out with the bottom.
Oh, okay. Thank you.
Okay, we cannot stop here. We're in moles. We need to get to grams. So we need the molar mass of silver sulfide. And that is 247.81 grams of Ag2S for every 1 mole of Ag2S. And tell me how many grams of silver sulfide can be made.
13.129.
13.129. We're going to go to 3 sig figs, so 13.1. Any questions? Only thing that's different about this is I've given you the the problem, and you're going to have to come up and do the reaction, figure out the balancing, and then go from there. All right. Yes. Mm-hmm.
How do we know that it's a double replacement? Is it just because of the reaction happening?
Just because of the reaction happening, yeah, you'll see that you have a compound and a compound, and then they just told us one, and so And it's a precipitation, so we only care about the one that became a solid. It is really hot in here. All right, what mass of iron 3 hydroxide is produced when 35 mLs of a 0.250 molar solution of iron 3 nitrate is mixed with 55 mLs of a 0.10 molar KOH solution? So what mass of iron 3 hydroxide? So that is my solid. And we are looking for grams. When an iron 3 nitrate, so FeNO3, is mixed with KOH. And we know we have 35 ml of iron 3, and it's a 0.25 molar solution. And KOH is 0.55 ml, and it's a 0.180 molar solution. And then before we can begin, we've got to figure out what our spectators are, and that would be KNO3. And then go and balance. OH, we need to balance OH, so we need a 3 in front of KOH, which means we need a 3 in front of KNO3. All right, so what's the first step to figure out how many grams of iron 3 hydroxide can be made? We need to go to moles. Yes, Kaylee.
Oh, yeah.
Oh, yes, sorry. I did that before, too. 55 milliliters. Yes, thank you. So we need to go to moles. All right. Does it matter which one we do? Well, what do you think? Kind of. So we need to find what? The limiting reactant. So we need to take both of them into moles. So 0.035 liters times, so 0.035 liters times 0.25 molarity gets me 0.00875 moles.
Yeah.
Okay. We're going to do the same thing for KOH, so 0.055 liters times 0.180 molarity gets me 0.0099 moles. So we're in moles. So what's our next step? So how do we figure out which one's limiting? Can we go ahead and figure it out now? No. Divide by the coefficient. So 1 gets divided by 1, which gives us 0.00875, and the other gets divided by 3, which gets us 0.0033. So who limits us? KOH is the limiting reactant. Good. So we found our limiting. Now our next step is to go back to the limiting reactant moles. So we're going to go to 0.0099 moles of KOH, and we need to take that to grams of iron 3 hydroxide. So for every 1 mole of FeOH3, it's 3 moles of KOH. And does it bother anybody if I go down to this next line? We're going to multiply that by 106.88 grams of FeOH3 for every 1 mole. So what do we get for our answer? How many grams of iron 3 hydroxide? 0.353 grams of FeOH3.
Does it matter if you put the 0 before the point?
No. Is everybody okay with that?
Yes.
Okay. So let's go one more, and then we're going to go to acids and bases, or acid-base titrations. From the previous problem, calculate the molarity of the nitrate ions in the solution after the reaction is complete. Okay, so how much did FeNO3 did we start with? What was the molarity of that? Okay, so the original was 0.250 molar. So that means Fe is 0.250 molar. NO3 is 0.250 molar, but we have 3 of them, so it's 0.750 molar. Everybody good with that? So we started out with 0.750 molar NO3 ions. So in my original, we have 0.750 molar NO3 ions. And how many mils did we have? 35 mLs. It wants to know what our molarity is at the end. So that's my X. So if you haven't noticed, we're doing an M1V1. What is my final mils? We started out with 35 mils, and we added 55. So my final mils, 90 ml. So solve for my final concentration. 0.292 molar NO3 ions at the end.
Why do we have to do 90
Because we diluted it, so we added more on top of that. Any questions on that? Okay, let's go to acid bases. So these are the ones that were bonus on your quiz yesterday. So calculate the molarity of sulfuric acid in a 20 ml sample, which is neutralized by 18.50 mLs of a 0.75 molar NaOH. So we have 20 mLs of my sulfuric acid, and I am going to take that 20 and I end up neutralizing it with 18.5 mLs. So the first thing to do is write your reaction. So sulfuric acid is H2SO4. And we react it with NaOH. When a acid and a base react, what are the two things we get? Water. So I'm going to write water as HOH plus a salt. And this salt this time is Na2SO4. We've got our equation. Now we need to balance it. So we need a 2 in front of NaOH and a 2 in front of HOH. And I write water as HOH in these just because it's easier to balance for me.
How did you get again? What did you say?
How did I what?
How did you find water? The two bases you said?
When an acid and a base. Now, I'm going to write everything I know from my problem. It wants to know the molarity of H2SO4, so that's my question mark. I know that we have 20 mLs of it. I know that the molarity of my NaOH is 0.750, and I know that there are 18.5 mLs. So now we need to solve. And so here are the steps to solve. Number 1. Start with your moles known. Number 2. Using stoichiometry, get your unknown moles. Find your unknown moles. And then number 3, you're going to go back to your question and find what are you looking for. Are you looking for grams, molarity, milliliters, what? So let's look at our problem. So we have a known and an unknown. So our NaOH is our known. So we can find the moles knowing molarity and mils. So molarity, big M, times liters gives me moles. So if I take 0.75 and multiply it by 0.0185, tell me how many moles of NaOH do we have?
Point 0139.
0.0139 moles of NaOH. Now the next step, so we have our moles of NaOH, and it wants us to find the moles of our unknown. So to get from moles of our known to the moles of our unknown, we need our mole ratio. And I'm just carrying this on straight through. You can start a new line if you want. You can do it in one big whole stoichiometric problem if you want. But this is just how I'm doing it. You don't have to do it exactly the way I do. For every 2 moles of NaOH, we have 1 mole of H2SO4. So right now in our problem, we have gotten to moles of H2SO4. So go back to your problem and tell me, what does the problem say? Molarity. So what is molarity? Molarity is moles per liter, right? I'm in moles. So now I can go to liters by putting 0.020 liters on bottom, right? I'm just dividing, putting it into the molarity problem. I'm just carrying it throughout. And what do we get as our molarity? 0.348 molar H2SO4.
So whenever you're referring to stoichiometry, you're just saying that you're using the mass to mole or mole to mass, or
Yep.
like just those kind of things.
Yep.
Okay.
Any questions on that?
0.02, that's from the 20 milliliters, right?
That is from the 20 milliliters, yes. All right, let's go to the next one then. How many grams of BaOH2 are contained in 25 ml solution if 16.52 of 0.85 molar HCl are required to neutralize it? Whew, that's a lot. So let's start with our equation. Barium hydroxide, BaOH2, is reacted with hydrochloric acid. And we know it produces water, HOH, and this time we're going to have barium, BaCl2. So the next step is to go in and balance it. We have two OHs, so we're going to put a 2 here in front of water. And we have 2 Cl's, so we're going to put a 2 here in front of hydrochloric acid. And we should be good. Next step, write everything you know from the problem. How many grams? So G, that's what I'm looking for. 25 ml solution. I know I have 25 mLs of it. If it takes 16.52 mLs of a 0.850 molar solution. All right, right.
The reason we write out the reaction, that's to balance it, right?
To balance it, yep. Because if you don't balance it, then you would just assume it's a 1-to-1 ratio, but it's not. So we got to get those number of moles. So now we need to, our very first step says moles known. So the first thing we can do is we can take HCl and get that to moles. So 0.85 times 0.01652 liters. .014 moles of HCl. And I'm going to move this up here so I have more room. 0.014 moles of HCl. So we're in moles of HCl. The next step says moles of unknown. So to get to the moles of our unknown, we need the mole ratio. So for every 1 mole of BaOH2, we need 2 moles of HCl. So right now, I am in moles of BaOH2. So now we can go to step 3. Step 3 says find what you're looking for. So go back to your problem. It says how many grams? I'm in moles right now. How am I going to get from moles to grams? Molar mass. So this time, we are going to say the molar mass of BaOH is 171.34 grams. And that's for 1 mole. So how many grams do we have? To 3 sig figs. 1.20 grams of BaOH2. Did we need the 25 milliliters? Nope. Yes. Because of the problem. 25.00 is 4 sig figs, and then 16.52, and then we have 0.850. Huh?
I thought those were exactly so they were. Like, what's the difference between
Okay. One more math problem, and then we're going to do redox, and we're done. If 25 mils of 0.625 molar HBr are mixed with 42 mils of 0.352 molar NaOH, what will the resulting solution be, acidic or basic? So very first thing, write your equation. HBr plus NaOH gets me HOH plus NaBr. So we don't have to balance it. It's good. Now let's write what we know. We know we have 25 mLs of HBr and we have 0.625 molar. NaOH is 42 ml and 0.352 molar. And it wants to know if it's going to be acidic or basic. Well, this is a strong base and a strong acid, and if they are completely neutralized and there's the same amount, then we can get, it can be a pH of 7. But this time we have different pH, not different pHs, different milliliters of them and different molarities. So this may not come out to be neutral. It wants to know if it's acidic or basic. So how do we know? How do we find out if it's acidic or basic? Whichever one is in excess. Good. So to find out whichever one's in excess, we need to find what first? The moles, the limiting reactant. So 0.025 times 0.625, and I get 0.0156 moles. If I do the same for NaOH, I take 0.042 times 0.352, I get 0.0147 moles. Now we need to divide each one by its ratio or its coefficient, which in this case is 1. So the limiting reactant is going to be, in this case, NaOH limits us because it runs out first. So we are left with some HBr in excess. So HBr is our excess. So this is, I heard it, somebody say, an acidic solution. Y'all all right with that? Good? Okay. So moles, go to your moles known, find your moles unknown, and go back to your question and see what it's looking for. Last thing we're going to do is look at redox. Just really quick, look at redox sign oxidation numbers, and then I am done. So 2 problems left. 15, or just 15 here. Okay. Redox. What does redox stand for?
Reduction, oxidation.
Reduction and oxidation. If your charge goes up, then you are oxidized. If your charge goes down, then you are reduced. Hence the reduction, a reduction in charge. Okay? So every free element has a charge. Everybody on the periodic table has, not a charge, has a number of what? Oxidation number of what? Every element up there has an oxidation number of what? They all have the same oxidation number right there when they're free elements. 0. This question asks, right here, asks that you find the reducing agent and the oxidizing agent. We're going to take that out. AP doesn't require that anymore. Okay, so they all have 0 if they're by themselves. So find the ones that have no charge, aren't hooked up with anybody. So the only one I see is copper. So copper's charge or oxidation number is 0. Any ion, it's by itself, has an oxidation number equal to its charge. So H plus has an oxidation number of +1. Copper 2 plus has an oxidation number of 2 plus.
Can you repeat that, what you said about any ion?
Any ion has a oxidation number equal to its charge. Okay, so next, any polyatomic ion like we have here in O3, the first thing is oxygen's oxidation number is always -2. So here, oxygen has an oxidation number of -2, and we have 3 oxygens. So what's that total oxidation number? -6. This polyatomic has an overall charge of -1. So what does nitrogen's oxidation number have to be to get us to -1?
Positive.
+5. So N is a +5. Again, let's go to the next one. Oxygen, always -2. We have one of them. So nitrogen, in this case, has to be +2. Go over to water. Oxygen, -2. Hydrogen, +1. Because we have 2 of them. That overall equals 0. So looking at those numbers, whose numbers change? You should find 2 elements whose numbers change. Nitrogen.
What do you mean by their numbers change?
Okay, so they said nitrogen. So nitrogen went from a +5, and over on the other side, it is now a +2.
Oh, okay.
And copper. Okay, so nitrogen goes from a +5 to a +2. Copper goes from a 0 to a 2 plus. So whose number went down? Nitrogen. So that means it has to be reduced. Yes.
Can you go over how you got 5 again?
On which one?
Nitrogen.
Where-
The left side.
Okay. So what I did is oxygen is a -2. Okay. And hold on, let me. So this is NO3 minus. So I know this whole overall charge has to be a -1. So oxygen is a -2. And we have 3 oxygens for a total of -6. So N, we got to figure out what N has to be so that my overall charge when they come together is a -1. So what number, when 6
Okay.
plus something gets me a -1?
Why doesn't the coefficient?
I mean, if you wanted to do the coefficients, it would just double everything.
Okay.
Okay, so we just kind of ignore the coefficients.
I hope you know how they can change the third plus 2, but the other one is +5.
Right, so it transfers electrons. So this is a whole transfer of electrons.
Oh.
So that's what the whole thing that's happening in oxidation reduction is transfer of electrons.
Oh.
Okay? So then that if nitrogen is reduced, then that means copper has to be oxidized. Okay, so your homework that I handed out a while ago is all over oxidation numbers. Do you guys want me to go through one more before the bell rings? This last one? We still got plenty of time. Okay. So first of all, the first thing I do is I go and I assign my free elements. So O2 is a free element, so it has an oxidation number of 0. And oxygen is usually always going to be numbered as -2, so I always start with oxygen. So oxygen, if I go to C2H5OH, oxygen is -2. There's going to be very rare cases where you see hydrogen as a -1. So I usually put it as a +1. Just because you rarely see it. So we're just going to go ahead and give hydrogen +1. This hydrogen over here is a +1, but there are 5 of them. So it's a total of +5. So I'm just going to go ahead. I have +5, a 5 and a 1, which gives me a total of +6. And I have a -2, so that means I need a -4 to cancel that out.
Wait, where'd you get 6? Oh, it's 5 plus 1.
Yes.
Minus 2. Okay. Wait, what about carbon?
That's where I'm going to.
Oh, okay.
So I have a -4. So carbon, my 2 carbons have to total a -4. So carbon is a -2.
I don't think we need
Wait, so for the hydrogen, we counted in it's subscript, right?
Yeah.
So are we doing the same for carbon?
That's what I just did.
Okay, and you were just writing down the 2s, just put it there?
No, it's a negative. The 2 carbons together have to be -4.
Okay.
So -4 divided by 2 gets me -2. Next, go to CO2. Oxygen's always a -2. There's 2 of them, so it's a -4. So this time carbon has to be a +4. Oxygen's always -2. Hydrogen's always a +1. And when you're doing them, make sure that they equal out to the charge that they're supposed to be. Water doesn't have a charge, so when I look at these and I multiply them, they should equal out to 0. So whose number changes? Carbon goes from being a -2 to a +4. And the other one is oxygen goes from being a 0 to a -2. So whose number went down? Oxygen, which means it is reduced.
So when oxygen's by itself, it's 0?
Yes. When it's by itself, it's 0.
is that for every element?
For every element on the periodic table has an oxidation number of 0 until they start hooking up with something.
Okay.
When they start hooking up with something, then if it's an ionic compound, then it takes the oxidation number is equal to its charge. And then when you start looking at covalent compounds, you've got to start looking at those numbers you know. I know oxygen is always -2. That type of stuff. Yes.
So it doesn't matter that oxygen appeared in every single.
But you see, oxygen here was a -2, and there's an oxygen that's a 0. Then I have an oxygen that's a -2 and an oxygen that's a -2.
So 2 of the -2s would just cancel.
So they just canceled out. There wasn't a transfer of electrons. Okay.
Trying to cancel out their stuff.
Mhm.
So you have to make it equal.
All oxidation numbers, when they come together in a neutral atom or a neutral compound, is 0, unless you have that minus charge like we did up on NO3. And then we have to finagle the number that we know and then go to the next one. Any questions? All right, so I am going to